Hello, everyone. And the last time we stopped at the definition of the radii of convergence, and we showed how we can express the smallest radii of convergence using the matrix of the connection. Now today we just to avoid confusion, we make some notation, and to avoid any confusion, just to precise when we are working with the, because the last time I didn't say for the connection nabla, for the spectral norm of the connection nabla, I didn't precise in which space the connection was acting. Because, for example, if we are working with this this K algebra, is a Fréchet algebra, it's not a Banach algebra, then there is a definition of bounded operator, but the notion of spectral norm, it doesn't really exist in that case. And here, when we are fixing, for example, a differential module over the algebra of analytic function over an finite domain, then when we extend this connection to the field Hz, then we just denote it by a blase. I'll just reset this MC. And there is another point that I didn't precise the last time. When we are working with the since n is has a is a free module with finite rank, then there is a term that said that even over a finite domain, any basis, any norm as an affinoid as an OX module are equivalent. But we are since we will from now on we will only work over we will consider MZ over HC, and it's enough to use the usual one, that any K vectors, any norm in a K vector space with finite dimension are equivalent. And we will consider the operator norm with respect to one of this norm, and then we can compute the spectral norm of our connection. is a Banach space because it is of finite. It's a Banach space over Hz. Then this means that any Cauchy sequence is convergent, and then so is for K, because it is a Banach space over Hc, then so is for over K, because Hc is an extension, not a finite extension. And since the connection is the connection is, not forget, is a K-bounded map. It's not Hz bounded map. Then we can compute the spectral, and since the spectral seminorm doesn't depend on the basis, then it's something that we can compute. Just here, last time I forgot to set, and the spectral norm is exactly the same thing. Then now if we want to compute the spectrum, then the norm and spectral norm, we start by computing the one for d over dt. Then as a map, that we consider d over dt. And we consider over Hz the absolute value. And for this absolute value, we have the following. And the norm of d, in that case, it's preferable to set d over dt, do not confuse. D over dt, in that case, is exactly the inverse of the radius of the point. And be careful, all these results are available when the field is algebraically closed. The computation is more easy because we can classify all the points z, that's why. And probably even if it's not algebraically closed, it should be the same. And the spectral norm is less than the norm, and in particular, don't forget, it's equal to 1. If the residual is the characteristic of the residual field is equal to 0 and equal to this, if the characteristic of the residual field is equal to p is strictly greater than 0. Then in that case, if we want to compute the Don't forget here we have to choose the derivative d over dt. Otherwise, we will not specially have the same we have. Then we can obtain this result just by developing everything, and we will get this result. And it's equal to the maximum of the spectral norm of just do not forget C nabla Z is over HZ and D over DT. Because the spectral norm depend on the derivation. We will see later when we focus on differential module over a differential field and a differential ultrametric field. And this especially is exactly equal to omega over 1 spectral radii. Then we observe that we can get the notion of the radii in a special case, in some special case, just by computing the spectral norm of the operator. The question is, can we do this to compute the smallest one? Can we do the same to obtain the other radii? The response is yes. And for that, we will express the other radii by using other connection that I will show just now. Then all the spectral Then for that, we know that we cannot express the differential module as a direct sum of differential module. However, we can consider the Jordan-Holder sequence of the differential module. This just means that we have a sequence and each quotient of the sequence is simple. And this just means, like as I said, then for all Then we set the differential to the quotient differential field. We have differential module. And they should have no, has no trivial, strict difference. Okay. We set E is dimension HZ E. RE is just equal to the spectral. And by performing a permutation by in the index, we can just assume that the sequence of RE are increasing, are decreasing. Sorry. No, are increasing. Can assume that then R1 less than R2. And by counting the value of we have an equality. R1 and spectral number of in the literature we can find, for example, that instead that they defined for example, in the book of Kedlayate, he defined the spectrality as here, and after he showed that they exactly correspond to the spectral norm as we defined it in the beginning. Then in this, I will just give an example of Jordan order sequence for the case, just a classical example to just observe have an idea what is it exactly, and to maybe to understand more why we have this inequality. It's need to prove better. Just set. Just to be careful when we are working with spectral already, we don't assume that Z is in K, because it's by definition equal to 0, and there is nothing interesting by studying such a value. And we will see after there is a specific point that it is really interesting to study the spectral radii, because the spectral radii in that case will be exactly equal to the radii of convergence. With A and B and some K, in K. And some K. Then the Jordan order sequence is that we have this injection from the exact sequence that we defined the last time. Then here, to arrive until here, all the quotient here, then the quotient here will be probably equal to the differential field of rank 1. Here we have B, and here we have A. And they are simple because they are of rank 1. We cannot find another, except 0, cannot find another differential submodule of this module. This is just a simple example to understand the difference. Then just give some notation and express when then by fixing Then we will say that in the case of, if we are in M radii, in the case if we say that the radii if it is strictly greater than the radii of the point, then we say that it is oversolvable. Second case, if it is equal to z, say that it is solvable. Strictly less. Spectrum. I will just give some example. For example, we will set, we will consider the for the simplicity, we will just consider x equal to an annulus, simple annulus, not a complicated one. Just 0, and here we put R1 and R2. And we consider the differential module OX with d over dt minus 1. This just corresponds to the differential equation. If we compute the kernel of this connection is exactly, we will resolve the equation y, the derivative of y equal to y. Then the solution is the exponential then in a neighborhood of each z, and it is the exponential of t minus z. And here we have just t minus z, I. Then in the case, if we consider z is a point such that equal to some AR and A and R is not is less than R1, then in that case we have Z is, then we have the disk, the closed disk at A and R is included in X, which means that there exists a disk which with in that case, he is in this disk. And in this situation, we have exactly the radii of convergence Rk is, sorry, and Rho. In that case, we have is exactly strict. It's not equal to the radii of convergence. Now, just to make things simple here, I will choose something like bigger than omega and put here equal to 1. Yes. And if we just start by studying this case, in this case, if R is strictly less than omega, then the radii of convergence over Z, Mi, in that case, is still equal to omega. There is no problem about that. However, in that case, we have the spectral radii is exactly equal to R because R is less than omega. No, it's better to write here something like less than omega. And this is still available. There is no problem about that. Because then we have this condition. Then if R is equal to omega, then the spectral radii is the radii is spectral, and in that case we have the equality. And in the case if R is equal to strictly bigger than omega, in that case also we have spectral radii equal to the radii. Then now just to give another example, and this is why in the case the first case, and this is the second case. In the case if for sure this should be less than R2. Then in that case, the disk cannot be in the annulus because there is the part of containing the disk 0 that is not in that disk. Just generally in okay, we have in this situation. It's not include. Or maybe strictly bigger. And here we have then in that case, we should have the biggest closed disk containing Z cannot can only be the in omega. As in that case, we have exactly equal to the radii of the point. And in that case, whatever the radii of convergence is, the radii of convergence is always equal to the spectral radii. And if then R is less or equal to omega, then we have, sorry, here is one. Here we are working with rank 1 equation, then everything is equal to 1. Then the thing that we observe that when we just focus on the spectral radii, we can lose some information. The question in the case if, then for any Z equal to XA R, we have, and for sure R is strictly bigger than 0. before saying that, if M is trivial, then just to have then for sure we will get the spectral radii all equal. It's trivial. This means that it's isomorphic to, this means just that it is isomorphic to OX T and here. And in that case, just have P C. The question that we can have, if we are in such situation, can we say that our differential module is trivial? The response is no, because and the problem is in differential equation, generally the problem is when the radii are solvable, or especially if the spectral is solvable. We cannot say too much thing, because it can be the radii of convergence, it can be over solvable or it can be only solvable. And in that case, if it is only solvable, then the equation is cannot be trivial. And there is a special case when we can say something about that, but generally the response is no, because because we have the following example. That it is strange and the most and the kind of example where we have problem with differential module. For the moment, they are the only one that we know having such kind of problem. And for example, if we consider X and we consider just in that case, just consider the analysis. Here's something and consider OX with d over dt, and here minus c over t, with c is a p-adic Liouville number. in the case of when the residue characteristic is equal to 0, such numbers that don't exist, and that's why we can have a classification in that case of differential module. However, for the p-adic case, it's quite complicated, because then here we have is p-adic Liouville number, and if then in that case, we have for any z in X, we have the radii of convergence. R1 is exactly equal to the spectral radii everywhere, and everywhere have this problem, and they are all equal to. Okay. And we know that this differential equation is not trivial, because we have this one, that it is equal to this one everywhere. If we want to have, if we want that such equation to be trivial, for example, we just need that, for example, for just like for this case, no, not exactly this case. If we consider this case for with the an example of such a case is just, for example, if I put here, for example, omega, and in that case, the differential equation is trivial because the exponential is defined everywhere. However, here is not the case. It's not defined everywhere. It's limited to the disk that we call the generic disk of Z. Oh, this is just an explication, and now, however, it has its own interest to consider the spectral radii, because then we observe that however, in that case, we don't lose any information. Yeah, to say that it is trivial, it should be equal to each. And the biggest radii of convergence is exactly strictly less than this value, and that's why it's not trivial. However, if we study the radii of convergence, the spectral radii of convergence, when the points satisfy this inequality, and they satisfy this inequality even in a very special case, that for in Prerequisite spaces we call it the skeleton of my affinoid domain. and it contains information about the curve. That's why it have its own interest to consider the spectrality. However, for other property on the radii, it's preferable to consider the other one. To have information about the spectrum. The thing is that it's we have some technique to compute the spectrality by using the spectral norm as many other properties that we will see later when we will consider a differential module over a field, over a complete ultrametric field. Okay. Differential module. Then we have just the is complete. And D is bounded. Then, and from now on, we just consider a differential field and complete with respect to an absolute value. from now on, we will just study the spectral norm and give some theorem that permit to obtain the spectral norm. After that, we will observe how we can, by using the spectral norm, because it is equivalent. As if we say spectral norm is equivalent to say that we can define the notion of radial convergence just by putting something like, but it's not exactly the radial convergence of solution. For example, in the book of Galois, when he said the radial convergence in the beginning of, in his definition, he just assumed that it is the he's just assuming that it is omega over the spectral norm of my nabla. Then proposition. Then as just example to observe that example of such a differential field, we can, for example, say that omega is something like hc over something gt over dt, and z, the radius of z is different from 0. Then proposition. This is the classical property of the spectral norm, and we then consider if we have an exact sequence, and for example, for this one, we can see it for differential for the radius of convergence. This just means in the case when we choose the derivative is equal d over dt, is just saying that if we consider differential module, and if it is the differential module is solvable, then so is for its dual. And the last one. And if we consider the tensor product of two differential modules, then their connection, the spectral norm of their connection is less or equal. With equality if the spectral norm of nabla 1 and nabla 2 are different. Sometimes the tensor product, when we are using tensor product, especially for when we are considering differential module of rank 1, then by adding two elements, the radius of convergence can be greater. For example, it cannot converge, and after that it can converge. It can be trivial, for example. Just I will give an example. Just the usual one. Then hc t over tt minus 1 and hc then in that case both just and with the radius of 0 r with r strictly greater than omega, to be sure that everything is working well. And then in both cases, this is nabla 1, this is nabla 2. Then the tensor product is also done. Here we have one element. Any element can be expressed like that. Then, because here is exactly just the derivative. It's just something like t 1 yes, plus 1. Then here is just something. Is f. Then we obtain d over df plus f minus f plus f. It's equal to d over df. Hence here exactly then the spectral norm of omega then the spectral norm of nabla 1. And here 2 is equal to over R1 spectral body and spectral body, and we know that spectral heat is exactly equal to omega, then it's equal to 1. However, here he just, this is nabla. So spectral norm of this one is exactly equal. Is equal to omega over R, and it's exactly less than 1 in that case. Now we will talk about the most important theorem in that case, that we call the proved for the first time by Jung, and after that by Crystal and after. However, and this theorem is also called the theorem of the small radii. Then when, in some sense, when the radii of convergence are too small, then the spectral norm of my connection will be exactly the same as we will just show it now. Then we need to consider a differential module, and it will exactly act like the matrix, the associated matrix in the cyclic basis, but it's just like the derivative is too small, then the operator acts exactly like the associated matrix in the associated matrix in a cyclic basis. And in that case, we can obtain our spectrality just from, if we consider the differential polynomial associated to this module, then the spectral norm will be exactly the maximum of the roots of this differential polynomial considered as a commutative polynomial. And this is really important theorem, because in the case because to compute all the spectrality, we will introduce we can always when the residual characteristic is different from is equal to 0, then this theorem holds, because if every time my radii, we can say every time my radii are small or they are solvable. However, in the p-adic case, it's not the case. They cannot be solvable and they cannot be small. I will explain what I mean by small radii. However, this theorem is available for any for any differential field with where omega is a complete Archimedean field. Let the algebraic closure be the root of, and this is just the commutative associated commutative polynomial. It has just I replace the d by t and put the same coefficient. Then the spectral norm of nabla is exactly equal to the maximum. No, sorry, just need to make another assumption before. If maximum of ZE is strictly greater, then here it's important, but it should be something, the norm of D as the norm of D as an operator. This should be strictly greater than the norm, not the spectral norm. And that is the problem, because there exists, because in characteristic, when the characteristic of the residue field is equal to 0, then the spectral norm is equal to the norm. However, in the other case, we have exactly that. We have exactly that, and this represents a gap in our theory that we need to use the Frobenius to generalize this problem, to obtain the more results about the spectral norm. And in that case, the spectral norm is exactly the maximum. Then the difficulty of this theorem is to prove that the maximum of the absolute value is exactly equal to, is strictly greater than D. However, we can obtain this value by using only by studying, we can obtain all the absolute value of ZE by just look at the coefficient of my polynomial. Here I will just put the maximum in that case. However, in the general case, there is we can use Newton polygon to get all the absolute value of the roots of my polynomial. Maybe if we have time, the next time I will explain how we can get to the root of a polynomial from Newton polygon. Then this is exactly. I will just explain it the next time. In particular, we know that if the I just will put this, if Z one are all equal, especially in the case, for example, if the polynomial is irreducible, then in that case the maximum we can obtain it directly. It's exactly equal to A0. Then there exists another nice theorem, which is just here. Yes. Just I said that I want to make the link between this and the radii of convergence and why it is. Then example. Yeah. Then here just the maximum of ZE is exactly equal to the spectral norm of G. And G in that case is exactly this matrix, the associated matrix in the cyclic basis. This is one point, and this result can be really generalized, and in some sense the derivative, this just mean in some sense that's why in some sense the commutativity, the default of commutativity is too small that we can say that it acts like the commutative polynomial. Then example. No, this is not an example. In the case of h z d over dt, this is important to choose this derivative. strictly greater than 0. In that case, the condition, then this condition just means that it's greater than R. Which means that the smallest radius of convergence, because we are talking about the just the smallest one. However, this volt, if all, for example, the absolute value of, then I can make it later. I will just set it later. Then this is exactly equal to omega over the maximum of one of this ZE, and this just means that it is less than omega R. Since we know that here, right, in p-adic, if then yeah. This just means that by small RD, we just mean that in that case, it's just less, it's not solvable. However, if the characteristic is equal to P, then in that case, we have something like that. And here we have omega R. And in that case, we know that it's strictly less than R. Then there are some radii that they are neither solvable, neither small. And this is just a proposition to extend this theorem. It's just a generalization to all the radii, because we can obtain them by all the here just we will take the minimum, just to say that all, then in that case I will just express it by and we just have that the spectral norm of nabla E is equal to some ZE, the absolute value of some ZE. maybe I should stop. And this means that all the radii are small. This means that all the spectral radii are less than omega r in the special case when we fix these differential fields. I forgot to say something. Then when all the radii are equal, we say that our differential module is pure. And for example, all the quotient of we say that after why we have that, all the quotient of Jordan, all the sequence are pure because they are simple, and we will understand why later. Just here, remark. If is pure. Then the next time we will explain there exists, like for polynomial, there exists a Hansel lemma for differential equation that permit to decompose a differential module. And if we can decompose a differential module, then we can construct as an exact sequence. And we will decompose our differential module by using spectral norm. For example, if we have more precise, you will not use the spectral norm. We will use the spectral norm in some sense, but we'll assume that if all the absolute value of the roots of my polynomial are greater than d, then if we have two roots that they don't have the same absolute value, this just means that we can decompose our differential module. And using this theorem, we can see after that we can decompose our differential module into a direct sum, not only an exact sequence, to a direct sum of differential module, pure differential module. No, there is a part who don't, but we generalized this for all the non-solvable radii. Then we can stop here for today. Is there any question? Thank you. Then see you the next time then.